Professor Clements with you as we consider Chapter 28, the second half of the OpenStax College Physics textbook. It's topics in special relativity, how we add velocities, what momentum and kinetic energy is like at high speed, why there's a limit on speed, and E equals mc squared. A few comments on that. So again, reminder on the postulates of special relativity. Einstein agrees with Newton, with Galileo, other physicists before Einstein, that you cannot do an experiment that will tell you if you're moving at 0 meters per second or 10 meters per second or 1,000,000 meters per second. The laws of physics, the experiments have the same result in all inertial reference frames. And again, those inertial reference frames have constant speed and constant direction, so constant velocity. Einstein's contribution, big contribution, saying the speed of light is the same for all observers. So here we have a raft going down a river, and if we're standing on the shore, the speed of this kayak would be how fast the person can paddle in still water plus the speed of the current. That would be a classical physics example, and special relativity tells us that at high speeds, the velocities do not add in the same way. So here's an example, again, of classical physics with the frame of reference the child is in going forward at 1 meters per second. We throw a snowball at 1.5 meters per second from the person. The person out here would measure a snowball coming in at 2.5 meters per second, and we can reverse the direction. Classical addition of velocities is to simply add the velocity of the frame of reference with the velocity of the object in that frame of reference. This is okay at slow speeds, it works all right, but at high speeds, special relativity tells us there's something different that happens, and we can see this right away with the frame of reference, the car, in motion, light coming out of that car at the speed of light, of course. And what would the observer on the sidewalk measure? Would it be speed of light plus velocity of the car? And this headlight is attached to the car. No, cannot be. The speed of light is the maximum speed that we can have. And Einstein developed a simple way to add velocities that prevents the speed of light from being anything else than the speed of light. So we can see this again with the rocket ship at high speed. Doesn't matter if it's a car or a rocket ship. 0.5 times the speed of light towards the Earth. We beam a laser towards the Earth. Person on the Earth will measure the speed of light as c, 3 times 10 to the 8th. And the person in the spacecraft would measure the speed of light as c. Doesn't matter which way the rocket is going, doesn't matter what the speed of the rocket is. The velocities add up in such a way that the speed of light is never different than the speed of light. So here's the formula that allows this to take place. We have v, the velocity of the moving frame that we might be watching, and w, an object in that frame of reference. So in the case of a rocket and a missile, here's the rocket speed, here's the missile speed with respect to the rocket. We add those up on the top just like we would in classical physics. The new part is this denominator. We take 1 plus the velocity of the frame times the velocity of the object in that frame. So we do that multiplication, and then we divide by the speed of light squared. This is the correct velocity for the combination of the frame of reference moving and an object in that frame of reference in motion. This is the correct way to do the analysis. The ordinary classical physics of addition of velocities on the top, a correction factor that prevents wrong results. So here's an example with the rocket headed towards the Earth, moving at 0.5 times the speed of light. This rocket can eject a canister, send it towards the Earth at 0.75 times the speed of light. So we would add these two together, 0.5 and 0.75 would be 1.25, and then we have to divide by 1 plus 0.75 times 0.5 c, and divide by c squared, so the c's squareds cancel. We have 1 plus 0.75 times 0.5, that's going to be 1.35 in the denominator, 1.25 up in the numerator, and I think I misspoke just a little bit, but multiply this out. 0.75 times 0.5 and then add that to 1 that's in the denominator. And this is, I've got a little error here because I use 0.7, I notice now in my notes, rather than 0.75. So I'm going to just quickly run that through again. So 0.5 times 0.75 would be 0.375 in the denominator that I have to add to 1. So I get 1.375 that I need to divide into 1.25. You should be doing this on your own calculator as well. So it's 0.909. No, it's not 0.89, it's 0.909. Hope you have your volume turned on. 0.909. I'll kind of, well, I can actually do this. It's not the best writing, but I'm going to try to turn on a pin here, and it wouldn't let me turn on the pin. 909 is what I'm doing here. Probably just should have rounded off to 0.91. But 0.909 is the correct answer. And over here, I think I have this one correct. So when we have the canister moving in the opposite direction, we do need a minus sign here. So it'll be minus 0.25 when you combine these two velocities, divided by 1, and minus 0.75 times 0.5. That gives us a 0.375. We have to subtract that from 1 in the denominator. Do this yourself. And I came up with minus 0.4c, but you better check my work. But this is the correct way to add velocities. You need this correction factor that Einstein gave us in order to get the right result for the relativistic velocity. Then momentum. When we do momentum in relativity, we find that we have a bigger momentum than in classical physics. This is when we're moving near the speed of light. And that momentum is gamma times the mass of the object times its velocity. So there's this factor of gamma that comes into play with momentum. A little bit more interesting, here's the, and because gamma is part of the multiplication, again we have this similar graph that we've seen before. When we get near the speed of light, gamma goes towards a very large number, infinity, and the momentum increases very rapidly. A little bit more interesting to talk about would be the effect of energy, so we'll head towards that. And when we get there, we're going to find that there's a derivation for E equals mc squared. There's an equivalence between the production of energy and the disappearance of mass. When mass disappears, we multiply by c squared. That's a big number, 3 times 10 to the 8th squared, times some amount of mass gives us an energy. And there are various mechanisms underway. Nuclear fission, there's a little bit of uranium that disappears, and we get energy out of nuclear power plants today. In the laboratory, scientists are trying to develop a fusion reaction where hydrogen will combine to form helium, and in that process some mass disappears and gives us a big energy output. So in the probably distant future, this might be a source of energy instead of burning so much coal and oil. In the sun, this is going on right now. Hydrogen is being fused to helium. A portion of the mass is lost. From the energy that comes out of the sun, doing E equals mc squared, you can calculate that 4.3 billion kilograms of mass is being changed to energy every second. 4.3 billion kilograms. So why doesn't the sun evaporate? That's a lot of kilograms, 4.3 billion kilograms. An ordinary human, is around 60 kilograms. Lot of mass disappearing here. Well, the sun does not evaporate because this is the mass of the sun in kilograms. This is 4.3 times 10 to the 9th. The mass of the sun is 2 times 10 to the 30th in kilograms, and consequently, this can go on a lot of years. Scientists believe it's been occurring for almost 5 billion years, and there's about 5 billion years left of fuel supply in the sun, this hydrogen reaction. Down here, nuclear power plant. Again, this is fission, the sun is fusion, and we'll study that difference in a future chapter. So here's our graph of kinetic energy versus speed. And again, because gamma is playing a role here, the relativistic kinetic energy increases rapidly, and we can't go beyond the speed of light. Classical physics, we can put any number we want in for the speed, and we get this kind of parabolic 1/2 mv squared, the green line. But the relativistic, the correct calculation, is not parabolic. It's much steeper. At near the speed of light, the energy goes way up. So a little bit on the energy down here. It turns out the total energy is gamma times the mass of the object times c squared. If the object is at rest, if the velocity is 0, what's the value of gamma? And you should be coming up with a 1. It should be a 1. So there's our rest energy, E naught equals mc squared. And the kinetic energy is calculated with gamma minus 1 times the mass of the object times c squared. Now gamma minus 1, gamma becomes a very large number, so it doesn't matter, it's minus 1. We head towards infinity. So how does an object obtain kinetic energy? Well, from first semester, you know that one must do work on an object to give it kinetic energy. So we'd have to do work on this object to give it, such and such units of kinetic energy along here. And as this red line heads towards a very large number, heads towards infinity, that means we'd need an infinite amount of work to get an object to have a speed actually at the speed of light. It would require infinite work. There isn't infinite work available in our universe, in our physical universe. So we can't, with our technology today, get objects to travel at the speed of light. That would take an infinite work to do so. Gamma goes to infinity, the kinetic energy would be infinite as v would head towards the speed of light. So there is a limit on speeds. C is the speed limit for the universe, 3 times 10 to the 8th meters per second. Nothing that has mass can go as fast as c. What does travel at the speed of light? Light travels at the speed of light. Light does not have mass, so it's not in violation of what I've been talking about here. So again, we have high energy accelerators that can accelerate electrons and protons to nearly the speed of light, but not up to the speed of light. And it takes very special technology and very low mass particles to get this result. But it is possible to travel very fast, but it is not possible to travel at the speed of light. That speed is unattainable, and unless we rewrite the physics books with some new understanding and replace special relativity, going beyond the speed of light, warp drive, hyperdrive, whatever you call it, in science fiction is science fiction. We can't travel faster than the speed of light, and that severely limits our prospects for the future of how far we can go in our galaxy and visit other stars. Sad but true. We can't travel faster than the speed of light. So with that, I'm going to stop. You should, of course, be reading the textbook, reading your reading guide. We've talked about how to add velocities. We must include a correction factor in the denominator, 1 plus the velocity of the frame of reference times the velocity of the object in that frame divided by c squared. There's a correction factor that keeps us from having objects that travel faster than the speed of light. The momentum increases. There's a factor of gamma in calculating momentum. It's not just mv, but it involves a factor of gamma. And we have this relativistic energy, and especially looking at the kinetic energy, it would take an infinite amount of work in order to get an object up to the speed of light. Just one last comment, the correspondence principle. If you notice this red and the green, they overlap back here. When the speed is small, then special relativity has the same result as classical physics. Special relativity is a broader theory. It's more applicable in different range of velocities. Special relativity and classical physics agree at low speeds. They agree at low speeds. So that's kind of the correspondence principle. This better theory includes the old theory, the classical physics, where there have been a lot of experiments down here that did not find any violation at low speeds of classical physics. Special relativity gives the same prediction at low speeds as classical physics. That's the correspondence principle. There's agreement. With that, time for me to sign off and let you go practice.